people as well, so the hospitality has been fantastic as well in my trip so far. So, as you can see, I'm not Scottish. My name's not Scottish. I live in Scotland, but my origin is from India, but I grew up in London, and then I moved to Scotland, and I run a group there. This is not the view from my office. This is actually where golf was invented, which is 5 minutes walk from the department. So golf is, I don't know how popular or not golf is in Lithuania. Certainly in the UK, in the south, it's obviously for people who are very rich and wealthy because there's no space. In Scotland, it's for everybody. Children play golf. It's like soccer or rugby. Okay, so it's great. So that's a beach here, and this is where the 18-hole game of golf was actually discovered. And if you're into golf, you'll know there are 4 major competitions. We've got the US Masters coming up, so 3 in the US, and there's 1 in the UK, and that cycles around the UK mainland. And every 5 years or so, it comes to St Andrews, and I think the next time will be 2021. So if you're in the neighborhood, drop by. So that's where I am. This is our group website. This is our Twitter handle. And what I'm going to do today is tell you about light. I'm actually interested in everything to do with optics. Our group works in a really incredible variety of things, but one of the big things that I did work in was optical trapping, or manipulation of particles, which, as you know, won half the Nobel Prize last year, and was a long overdue recognition for something that has quite simply revolutionized the way we do a lot of science in biology, medicine, and fundamental physics in ways that will surprise you. The first paper in that was in 1970. And a field that survives 49 years is a great field because it means it's got something to add. It's not so displaced by another methodology in science. It's a technique that survived 49 years and we're still pushing the boundaries with it. It means there's something good to it. And I hope to give you a glimpse into that today in the next 50 minutes or so. So this is where St Andrews is. It's a small place. It's very small. The town is 10,000 people. The university is only 8,000 people. We're here, which is actually the sunniest part of the UK. So statistics, we can make you do anything for the tourism. And that's the golf course we just saw, and that's my building here in physics, and that's medicine. So I'm lucky enough to have laboratories in physics, and we have medicine, we have a nice bridge, so we don't have to walk outside and bear the cold Scottish weather to transport samples across. So we enjoy that very much. It means I lost my view, but the exciting thing is everybody's close together and we can do lots of interdisciplinary science as well. And the weather's probably not too dissimilar to here, so you probably know what we're talking about. St Andrews is the 3rd oldest English-speaking university in the world after Oxford and Cambridge, and it's the #1 university in the UK for matchmaking. So because it's a small town, you're most likely to meet your future spouse at St Andrews rather than any other university in the UK. Now, I don't know any statistics for how long people stay together or how happy they are, etc. But anyway, that's a funny statistic that we have. And as you know, our future king and queen met there a while back. They didn't do science, I should add. Anyway, so what do we do in my group? So I've been interested in all areas to do with light. And, light has a privileged place in the universe. If we think about light, and when you think of Einstein, you think, well, time and space. You always say, the speed of light is a constant in vacuum. Right, that's a real tenet we could put in the ground and say nothing's going to change that. Okay, and we try and prove that's wrong. But that's actually the basis from where we say our understanding of time and space can come from. So light has a very special place in the universe. And it does so many beautiful things, and I'm sure many of you are working in it. I'm interested in a lot of areas. I'm actually a quantum physicist by training. So I just learned biology out of a textbook. But what I do now is we're going to talk a little bit about manipulation. We do a lot of work. This is not what I'm going to talk about today. But we now do a lot of work using special beams to image organisms for biomedicine. And this is an emergent and very exciting area. So here, for example, using special beams of light, not too dissimilar to Bessel beams, but this is an Airy beam. You can see here, you can see more structure for the same optical dosage than a Gaussian beam. And this instrument, for example, has been commercialized from my lab and is now in 15 laboratories around the world and looking at cancer diagnosis. So I'm very excited about that, to translate things, and we can talk about that maybe later in in the open session if anybody's interested. I'm also working on new ways to look through tissue. So my group was worked here. This is the one big thing light cannot do. So light can image small things, big things, but the laser pointer won't go through my hand. How can I go deeper with light? Through scattering media. That would change a lot of what we'd want to do with light. And that's something we're working actively on, and this is one of those things that we do there. So that's what we do. Now, today, what I'm going to do is I'm going to talk about the work largely of this gentleman here, Arthur Ashkan, who is 96, was the oldest Nobel Prize winner, I believe. And most of you, if not all of you, probably were at Gerard Maroux's talk yesterday. I don't think Donna Strickland could make it. And so they jointly shared the prize, as you know, for chirp pulse amplification. But the other half of the prize, though, of course, the two methods are slightly different. They're both in laser physics, but obviously they have quite different fundamentals. Ashkan came up with the very evocative and the very simple idea that light can move an object. So the idea is I take this bottle, I shine this laser pointer and the bottle moves. It does something. Of course it doesn't. I mean, I moved it with my hand there. It wasn't a laser pointer, right? For those watching closely, I'm not a magician. But we all know intuitively, when you go into the laboratory and you turn on the optics or the laser, the optics don't move. So the force of light is very, very small. Okay? So we'll see in a moment how small that is. But it's so small, but small things are beautiful. Small things are important. So in fact, optical traps can make some of the best force sensors we know, have measured the most exquisite displacements and force displacements known to man from single molecule biophysics, and continue to challenge us in what we can do. So that's what we're going to explore today. But as it's a broad audience, I'm going to give you some really interesting basics and make sure we all follow where this idea comes from and why we might need to think about it. So let's go back basically 400 years to the time of Kepler, and with Tycho Brahe on the little island in Ven between Sweden and Denmark doing his observations, and Kepler looking at his laws of planetary motion. He was also interested in how the tail of a comet points away from the sun. And this is actually a sort of hypothetical meeting between Aristotle, this guy Hevelius, and Kepler discussing the tail of that comet. And Kepler wrote this, and a time before we didn't really have our ideas of light propagation fully understood. He was talking about the light from the sun striking upon the comet, penetrating and drawing something away, pushing something off. Okay? And this track of light, and it's breathing out its own tail, and the comet's, if you like, consumed or destroyed. So here, this was the first idea that something from the sun, the light from the sun, could push on the comet and push off material. So if you like, maybe that was the first time radiation pressure or light pressure came to the fore and people thought about it. Of course, like many ideas at the time, it was way ahead of its time, and nobody believed him and nobody could understand that. And you can see that here in the NASA video of a SOHO video of a comet's tail, which is pointing away. It doesn't point quite away from the sun for a number of more interesting physics reasons, but it definitely doesn't point towards it. Of course, what we had to do, though, is wait for a little while to understand how we could do that on Earth. So let's do a little interactive thing. Okay, so here's a little question just from a simple book, which some of you might have read thinking like, so I'm going to get you to do some work. So I've got a rubber and an aluminium bullet and a piece of wood, and I just would like to knock the block over or damage it. So I've got the same bullet that comes out of the gun, but one's made of aluminium and one is made of rubber. And I'd like to know which one is going to do two things. One, which is going to knock the block over? Is it the rubber bullet, the aluminium, or the same? Who thinks it's the rubber bullet? One person. Who thinks it's the aluminium bullet? 3, 4 people? There's no D, so I'm going to assume everybody who thinks they should be the same if they come out with the same speed and mass. 3 people. So that means about 90% of the audience are too nervous to answer. Okay, that's very interesting, including many more senior people. All right, let's move on from that. Okay, this is not a trick question. All right, they come out exactly the same speed and mass. One's just made of rubber, one's made of aluminium. It's pretty simple, right? Which one's most likely to damage the block? Who thinks rubber? Oh, yeah. No, okay, who thinks it's aluminium? Right, that's the biggest consensus we've had. And who thinks they're both the same? All right, so there's no, oh, they're saying, right, okay, so let's think about this. This is very simple physics that everybody should know. Okay, so what is the physics here? When we try to knock something over, we need to exert a force. And force is a change of momentum. All right? So if I take, let's now forget bullets, let's think of a squash ball. Squash, right? Racket game. So if I have a ball that comes with mv, it hits this, a rubber ball, and it bounces off, it leads with minus mv. So what's the change of momentum for this? 2mv. Right, now let's say I put an aluminium bullet or an aluminium ball or something onto this. It's going to come on. What's the aluminium going to do? It's likely going to get embedded in the block. It's going to stop, or it's going to damage, or it's going to set on fire, or cause a crack. So what's going to happen is the aluminium bullet is going to come along and go, boof, stop. How much momentum has it transferred? mv, right? So the rubber bullet transfers twice as much momentum as the aluminium. But the aluminium one is going to transfer all its energy because the rubber bullet is going to come with half mv squared. It's going to leave approximately with half mv squared for a near elastic collision. Whereas the aluminium bullet is going to transfer all of half mv squared to my block. So the first answer, the correct answer is the rubber. And the second answer is the aluminium, all right? Where does this come from? It comes from our understanding of energy and momentum, all right? Very simple, all right? And that's why we go back 100 years and we understand the interaction between the electromagnetic spectrum and electrons, and we look at work at Compton and Frisch, but make sure you know the difference. Now, why did I jump from comets to rubber and aluminium bullets? We're not doing anything with bullets. Well, when Ashkan in the 1960s started and everybody was making lasers and looking at second harmonic generation, he wondered about the idea of light bouncing off a mirror. That's essentially the same as my bullets, whether they be rubber or aluminium, bouncing off the wood. Okay? So my bullet now is my photon. All right, so he said, what's the force on that mirror? And this is why your optics doesn't move in the laboratory, if you're interested. All right, when you turn the laser on. Okay, so if you do that and you put the numbers in, the average number of photons, energy of a photon, momentum, incredibly, the rate of change of momentum is independent of wavelength, and it's just 2 times the power over c. You take a 1 milliwatt laser pointer, so that's 2 milliwatts divided by 3 times 10 to the 8, that's 6.7 piconewtons. 6.7 piconewtons, 10 to the minus 12 of Newton. What is a piconewton? It's the gravitational force of attraction between you and your laptop. It is not something you need to worry about. Okay? So they said, oh, let's forget this. This is crazy. So that's why when you turn the laser on, a piconewton force on your mirror optics, who cares? Right? That's why when we stand in sunlight, we recoil maybe for other reasons, but we don't from the momentum of light. But what Ashkan realized was, and other theoreticians like Gordon, was that when you reduce the size of an object, its mass drops very quickly. If I take an object and halve one of its dimensions, a sphere, if you halve a dimension, the volume goes as the cube. For the same density, it drops by a factor of 8. So if I drop something by a factor of 10 in one dimension, its mass drops by a factor of 1,000. So Ashkan realized, if we have a very small force, let's forget trying to move a bottle or a glass of wine or a beer or a glass of water or an optic, let's move something very small, because we've got a small force and let's measure small things. And that's where the genius was, because if you put that in, you should get nice accelerations actually at the small scale. So he said, let's forget macroscopic objects, let's go to micron size or even smaller. And this is really, really interesting, because this led to things like the scattering force. So this is an actual video by Yuri Milner and the late Stephen Hawking showing how we're going to get to the nearest star using light pressure. This is actually true. Mark Zuckerberg has now joined the board. And what we're saying is we can't send a spaceship at the speed of light to Alpha Centauri. It's 4 light years away. So what we're going to do is send little specks of dust, or little computer chips essentially, with big sails, and we're going to use lasers to push them. Now this sounds absolutely crazy, using exactly the same argument I just showed you. That sounds mad. It's absolutely true. There's a £100 million project on this. And believe it or not, it could get to Alpha Centauri in tens of years. So what you do is, rather like a plant, you just sprinkle these little laser chips, and they open up, and the laser cell pushes one of them, and one of them gets there. All right, now, I'm not here to justify this idea, but it's an idea, and it's actually the most sensible, believe it or not, idea currently to get to Alpha Centauri within tens of years. Who knows? It might work. So, the size scale is not this size, but from that idea, and of course the original work of Ashkan, Gordon, and others, we know that the size scale where we can really make a difference to optical forces is the size of a human hair or smaller. So what we're going to do is go down from here to here. And the red blood cell and even single molecules is where optical traps have made a difference. And this is why, since 1986, with Ashkan's first paper in Optical Tweezers, so he did a first paper in 70, and then we'll talk about that, and then his progression to what's really optical tweezers, single molecule biophysics has been changed, has been revolutionized. It's probably the most powerful optical technique to have influenced biologists in the last 30 years. And the reason is we can now understand single molecules and look at their reproducibility, build up statistics, and look at the heterogeneity of life. You know, having slightly different molecules, etc., all under a microscope. So how do we do this? How do we create a trap, though? Because I'm just at the moment looking at reflection of light or reflection of bullets from a surface. So the first trap, and this is a great experiment, if you've got a laser in your lab and a glass cylinder, you can actually just take this bottle, chop the ends off, tip the water out, and then just shine the laser from the bottom, make sure it's eye safe, put a nice laser beam block, and then just take a little perfume or aftershave or some spray little droplets. And you can see on the right, that's what happens. They come down, and so every so often a droplet stops. You can do that with 10 milliwatts, a few milliwatts of laser light. And what happens is air currents knock it out. What's happening there? The very same radiation pressure that was sending my chip to Alpha Centauri is now basically balancing the gravitational force, basically, or the weight, if you like, of my little droplet. Okay? And you can do that on a nice sunny day. This is a colleague of mine. We did this experiment in Illinois Wesleyan in the USA, which is a lot of fun, and you get very wet, but it's the same idea. So there we've got the jet of water holding something up. Now, that's fine. I could do that. That's optical levitation. I could hold something against gravity in air. That's fine. But that's not really very satisfying because I've got air currents going around and I'm also relying on gravity. And I don't know the mass of a cell or a molecule. I'd like to hold something maybe a little smaller and a little bit more easily and controllably. So what the first idea in optical traps in 1970 shifted this round. And what happened, and this is the fiber optic version of that, was instead of levitating something this way, it put something in liquid, so you have a natural buoyancy, and then it shot 2 laser beams from the side. Hardly any optics, just 2 optical fibers. And here we have that. So this is exactly the same experiment, and you can see here on the right, this video is from Monica Rich-Marta's group in Innsbruck, for example. You can see 2 single-mode fibers. There we go, and there's the fiber core, and you can hold a particle in between. It's really simple. There's no lenses. It's just 2 fibers. You can buy them on Thor Labs, get another snack box, and there you go, you can just do that. And there you go, so this is not optical tweezers though. It's rather like me standing here with 2 jets of water trying to hold me here. And so I'm sitting in water, and 2 jets of water light are hitting me and holding me here. Now, of course, you can understand by changing the laser coming in through each fiber, I can move the object left and right. That's great. I can distribute the force. You can displace the fibers and have different equilibrium position. But there is another force acting here which I'm not telling you. So far I've just said the light is scattered. But of course, if I have an object like this, the light is also, for simplicity at the moment, is bent through the object. It's refracted. And that refraction or gradient force is the other force that stops it moving, if you like, up and down the screen. All right, so it stops it leaving, if you like, in this direction. All right? So that's great. So that's the first really simple trap. That's what Ashkan did in 1970. And this trap is still used very, very widely. Let's have a look at where this is used. So let's have a look at something really, really interesting. So the momentum of light depends upon the refractive index of the material. It can be written like this with the Minkowski formalism. There's also the Abraham formalism. I won't go into that here. But very interestingly, something funny happened. So let's say I took this water bottle and I emptied it of water. I took the lid off, and then I shot 2 laser beams at it to hold it. What do you think is going to happen? This is a deformable object. If I take a beach ball, slightly inflated beach ball, and shoot 2 jets of water, what's the beach ball going to do? Compress. Believe it or not, light does exactly the opposite to a cell. A cell bulges out, it gets fatter. Why does it do that? It does that because the refractive index of a cell is higher than its outside. So the momentum of light is bigger inside. So at the surface, there must be a momentum outwards. So when you put a cell into an optical trap, it expands. All right? It gets squeezed. Amazing. Who's squeezed fruit in a supermarket? Right? You can do that optically. Now, why would you do that? So let's look at the physics. Like a good physicist, in this paper here, Joachim-Gruck's group modeled the cell as a block. But you can see the red arrows point outwards. And if you see that calculation, if you say the cell is 1.37 and the refractive index of water is 1.33, you get a bulging outwards. So when light enters and leaves a dielectric medium, its momentum increases and it falls outwards, away at the surface. That's interesting. So what he did was he created this. He created this to look at mechanical phenotyping of cancer cells. So here, the cells just flow. They're held between 2 fibers, and they're squashed, just like you're testing fruit. If you're testing an avocado or a nectarine or something, I don't know. And you can see the cells get squeezed. And then you measure the ellipticity of the cell. And what happens is, as you know, when people develop cancer, the cancer can metastasize. That means the cancer can migrate through your body to one of the larger organs. And the cell's mechanical phenotype, if you like, they become more squashy and mobile. So the mechanical phenotyping was different. This is how the distribution of the deformability varied for 3 types of breast cancer cell, just using this idea of simple momentum of light. There's nothing added. So this has actually also been tested now and is used for oral cancer. So cancers that are hard to pick up. So you can take a swipe, take a few cells, and literally, just like squeezing a water bottle, squash this. And each time you squash it, you can look at the ellipticity and see what's happening. So that's one thing you can do, and that's known as a cell stretch, which is used now in many labs around the world. But you can do other things with this dual beam trap. So you know how sometimes people tell you, nature knows best? Physicists, scientists, we try and create exotic materials, exotic systems. But you know, we should just follow Mother Nature, because nature's always got it down to a T. You know, if you let nature design a camera, everybody here in this room takes their eyesight possibly for granted, perhaps, or has beautiful eyesight, which is fantastic. But did you know, in front of your photoreceptors is a horrible big layer of cells and tissue? It's rather like designing a camera with all these pixels and putting a big scattering media right bang on top of it. Who would do that? Nature did. Nature did that. That's what your eye does. That's what my eye does. I still don't know how I see. So how do we see? Well, there were these cells, known as glial cells here, that go from this top layer here down to the photoreceptors. You see that there? These cells here. Nobody knew how those cells operated or worked. So what this group did here, this is Joachim Guck and Franze, about 12 years ago, is they took one of these cells from a mouse model, and they put it between 2 fibers, just like the optical trap. The fiber, just like that sphere, lined up between the two beams, and then they said, well, let's just see what the other fiber collects, how much light that collects, compared with and without the cell. So they said, is the little cells in your eye, are they little miniature optical fibers? And indeed they are. And you can see here, they can measure the transmission of a little cell in your eye with that sort of accuracy and measure nanowatt transmission. So this resolved a problem in biology that was hundreds of years old with the simplest trap that you know so far. Very elegant, very powerful, but could not have been done another way. So that actually has now started to help our understanding of eye disease and actually understand what happens when those glial cells get damaged. for people with optical conditions. So that's a dual beam trap, but that is not optical tweezers. So optical tweezers is specifically a three-dimensional trap. So people started to think, well, you know, two traps, two beams to hold this. Can I not just pick this up and move it around with one light beam? Let's make things really easy. How would I do that? So there we need to invoke the other idea that I've already mentioned, but in a little more detail, and it's not just think of the scattering of light or the bouncing of light off the object, but also the way the light passes through the object. And here we need to think of Newton's third law. So every action has a reaction. So let me take a sphere, and let me ignore the scattering component for the moment, and let me pass two rays through the sphere. Okay? I pass two rays through. The ray at the top is a thick ray. It's a lot more energy than the ray at the bottom. It's really simple. And it's just like that other question. It's not a trick question. You can see the ray at the top goes through, and for a higher refractive index, it's bent down. The ray at the bottom is weaker, and it gets bent up. Is that okay? Yeah, it's fine. Is there a problem with that? Not really. Well, there is really. As a physicist, you say, well, if I draw a diagram like that, I'll say, well, I need momentum conservation. So I look at the momentum on the left and the right of the sphere, and I say, okay, what the sphere has really done is bend more light down than up. It's created an imbalance in the vertical direction. I hope you agree. All right? Now, if I've done that, if that sphere has made the light bend down, the sphere has to go up. And which direction does it go? It goes towards the stronger light beam. So this is known as the gradient force. And that gradient force, therefore, pulls particles into the brightest part of the beam. And so Ashkan, 16 years after his first paper in 1970, in this famous paper here, the most highly cited optics letter ever, discovered optical tweezers. So we take that idea, and now with a single beam, we focus it down, and it has a bell-shaped or Gaussian curve, and we can see the sphere bends light in one direction, so the sphere moves in the other direction. So if I shine this laser pointer down on this will get pulled into the beam, and I should be able to do this. I can hear a sound, though. Oh, it's rubbing on the table. I don't like that. How can I lift it up as well? I'd like to really lift it up. I'd like three-dimensional control. Do I need new physics? Not really. And the reason I don't is because what I need to do is just think of the gradient force, not just in XY with the bell-shaped curve, but to do that, as you can see on the left, I've focused the light beam down with a high numerical aperture optic, probably to a micron size. In the very process of doing that, you can see in the diagram of the light, on the right, I've got rays coming in an angle. All right, it's high NA. And they leave the object going down. So in other words, what I've done is the object has not only bent the light either left and right, but it's made the light, if you like, go down. It's increased the downwards momentum. So the object must come up. So it comes up to the focus. Now it sits just below there, because of course I'm ignoring the scattering component I started out with when we discussed the bullets. But if you put that all together, what happens is you get a three-dimensional trap. And that's here. There's your equilibrium position. What do we need to know? The scattering force, that's like bullets, rubber, aluminium is proportional intensity. This gradient, I've just told you, is proportional to gradient, but it's also proportional to a parameter called alpha. Alpha is the polarizability. So if you do electromagnetics, many of you know the polarizability of a dielectric object is proportional to its volume. So if I go from a 1 micron bead, or object, to 100 nanometers, the polarizability drops by a factor of 1,000. So it's very hard to trap dielectric objects that are very, very small, unless you go to a different material, like gold or something. That's what you do here, okay? And this equation is really I think, the reason Ashkan won the Nobel Prize. All of that is beautiful, and as we'll see, the reason is this is the world's, I guess, most exquisite Hookean spring. Force is proportional to displacement. It really comes down to that. Every time you do an oscillations and waves course and you do a simple harmonic oscillator, you think about that, that's what it comes down to. But the beautiful thing is we can now functionalize this bead and use it, if we know kappa, to measure displacements and forces to an unprecedented degree. Let's see how that happens. So let's just see some objects moving, because that's what everybody likes to see in tweezers. So there we go. There's a large object on the left moving. So that's a 5 micron bead. So there you go. We can move it left and right. This is very easy. We have 3 or 4 of these in the undergraduate laboratory. It's actually amazing for a student to see that light can have a momentum and exert a force. Absolutely incredible. And on the right, though it might not work, let's see if it does. I don't know if some of you might be able to see that. You can see this bright blob, and that's silver particles all collecting. And for those of you perhaps at the front, the lights are a bit dimmer, you'd see all these colors because all the particles are slightly different in size and they have a plasmonic response. And it's white in the middle because it's an accumulation of different sizes. And so there, that's trapped there. But please remember, the reason we can trap these is because this is very large. If I had this particle at this size, that would be a lot tougher. All right? And that's why people go to exotic materials as handles. All right? Now, I don't want to spend a whole time just talking about the basics, but we basically use light in the near infrared of the spectrum because that's less heating. Some of you know it's called a therapeutic window. It means when we're doing biological studies on cells or tissue, we have minimal damage. So people typically use optical tweezers between something like 780 nanometers to 1064. You can do it at any wavelength, all right, so long as you've got a sample. And these are all done in liquid. This is an example of what the forces look like for those interested. Just very quickly, there's the scattering force. If we ignore absorption here, and that's our little focus bead that we've just seen, you can see here the dependency on wavelength, but it's proportional to the intensity, and the gradient force proportional to del I, and the volume, once again, with that dielectric. So that gives us the basic physics of why we can trap things and why we can't trap other things. If you want to do this exactly, you need to use a Maxwell stress tensor model, which I won't go into here today. So this is how you actually characterize a trap. You just watch the particle wiggle. So it's trapped, but it's undergoing some Brownian motion. So it's moving around, if you like, in this bowl, this optical bowl. And if you do a probability displacement, you get this beautiful curve here. This is one that Eric Dufresne took a long time ago now. And it follows a beautiful Boltzmann law. And if you do that and look at the probability, you can find from the thermal energy, kT, you can find a form for the potential, U. And so, by just watching the particle, we can find U. And we know the force is minus del U. Okay? In other words, it's the differential of that. So that's where the beautiful idea of the parabolic potential comes from. And that's what we have. So we have a particle trapped in a near-perfect Hookean spring. It's like a little parabolic potential. And there it is, measured out for you over about a couple of 100 nanometers either side. And trap stiffness is linearly proportional to power. And that's the equation you need to remember. That's it. So, and in the idea that most experiments are done in liquid, so this term, the inertia doesn't matter. These two, if you like, largely dominate what we're going to look at. That's all very well and good. What can you do with this? You can do incredible things. So Ashkan does not have the highest cited paper in optical tweezers. Have a look at them. There's many biology papers that are much more highly cited. This is an example. Kinesin, okay, is a molecule, all right? And this helps shift chromosomes and other work in your cells. And what happens is they move along little tracks called microtubules. And they do this measurement and this funny walk, this inchworm walk across there. Biologists never knew how this worked. And how does it work? It converts ATP to ADP phosphate. Okay, so you can watch a single molecule reaction with the energy less than 1/10 the energy of a photon in a real room temperature apparatus. So what they did here was they used optical tweezers to hold a bead, and the bead was the carrier. So the kinesin dragged the bead along, and it just nudged every time it did it. Okay? And there it is. And you can measure 8 nanometer steps. Now, believe it or not, and you may not, this might be quite surprising to you, the displacements you can now measure in current apparatus is equivalent to the Bohr radius of the atom. Now you might say, well, hold on, we only just got super resolution. How can you do that? It's because you can use elegant techniques to measure the center of gravity of a single object. Resolution in super resolution only comes when I have 2 objects or more. If I have 1 object, If I can use beautiful methods to determine the centroid of that, I can measure very, very small displacements. And here, for kinesin, they understood that you could actually, it went in 8 nanometer steps, and they resolved the biological mechanism, it did that. Now you might say, well, why didn't we just tweeze the molecule directly? Why do we need the bead? Well, that's a great question. You can tweeze the molecule, but it's very hard. Once again, because this alpha parameter is very, very small. So it's much easier to take a symmetrical object that I know and calibrate and use that as a transducer, force transducer, that then nudges along every time that I'm measuring that. So that's the kind of thing you can do. Time for a video. So this is a single piece of DNA tied in a knot. So this is a fluorescent piece of lambda phage DNA. This is taken from Stephen Quake's group, but the first experiment for this was done in Japan, but they didn't have such a nice video. And here, what you're doing is you're attaching 2 traps to the end, and then you basically tie a knot in a single molecule, rather like tying your shoelaces. You can do that with optical tweezers. And so what they do is they use biotin and streptavidin to make a linker to attach to one end of the molecule and the other, and they hold them with 2 traps and then tie a knot. Now, they're not just doing it to show that they can tie a knot. There's actually a lot of very, very interesting physics. As you may guess, all your molecules in your cells are being knotted and unknotted all the time. Okay, so there's special enzymes in your cell, topoisomerases and other things that are actually knotting and unknotting your cells all the time. What they were looking at was basically trying to kill cancer cells with knotting. In other words, the way a cell dies matters. You know, cells can self-program themselves to die, something known as apoptosis, which you might have heard of. And they were looking at how they could program cells to die by depriving them of certain enzymes and molecules in this situation. But I think that's a really beautiful example of what one can do with optical tweezers. So what we're going to do now, if I've got time, and hopefully I have. I don't know what time it is. Yeah, loads of time. Yeah, is we're going to go on to how to make many traps and not only just move something left and right and up and down, but make it go round. Okay? Which has become a very, very interesting area. So this has actually been used for, this is like multiple traps. And we don't have little beads with our university logo on. I just made this little GIF. And the red spaghetti is actually the polarization of light as it's propagating through there. So we're going to actually have a look at that in a little bit more detail. So how do I create multiple traps? So that's my name, and it turns out, this is a bit spooky, my name is actually an anagram of Ashkan. So that's quite funny. So unfortunately, the Nobel Prize Committee weren't dyslexic, otherwise I might have had a shot there. So, so how did we do either of these videos? The right-hand one is David Marr. We took a laser beam and we time-shared it. So let's say there was a laser coming through the ceiling and tweezing each of us. Now, what would happen is it would tweeze me, then go to you, and then go all the way around, and then come back to me. Now, that sounds like a very stupid idea, right? Because you'd say, well, wouldn't you just walk away, Kishan, by the time the laser got back to me? But acousto-optic deflectors are very, very fast. They work at kilohertz, tens of kilohertz, and that means, basically, to the naked eye, you can see the Brownian motion there of the bead? We can actually stop it. It's so fast, the AOD, it's essentially as if I didn't have any time in between the laser going all the way around and coming back to me, time for me to diffuse away. And you can do that, and that is still the most popular way to actually do multiple traps. It's very powerful. I've just put a table here from a review we did for these time-sharing devices. You can use electro-optics or piezo or galvo, and there's pluses and minuses. I won't really go into that, but if you're interested, please look at that paper there. But it's very, very powerful. Very powerful. And in the right, you see David Marr's group making one of the first little valves the size of a heart valve, all with optical tweezers. So they made a little pump, just with little beads, held and spun. So you can see the particles, they're spinning either way. Now that's great, but you can see that maybe we've got 100 people in here or 200 or whatever. There will be a limit at one point where I will diffuse away. So how do we work that out? It's beautiful. You can do lots of fun stuff. This is a St. Andrews thing anyway. So we can play golf as well on this miniature scale. And unlike my golf, you can always get a hole in one anyway, so there we go. But the physics of this is actually very, very interesting. So if you've ever spun a plate, just like me going from each one particle to another, what we're doing is we are spinning plates or trapping particles. So there's a diffusion time. Einstein's famous square root 2 dt. Really great little calculation to do as a student. Put the numbers in, a 1 micron bead in water, there's a diffusion. Let's say the laser takes 25 microseconds to go all the way back around and come back to me. So I will diffuse 5 nanometers. Okay, if I'm a 1 micron bead, you say, well, who cares about 5 nanometers? Well, if you were doing a measurement on kinesin, you would. You're trying to measure 8 nanometer steps. So that starts to become a limitation. All right, so that's the kind of accuracy that you can get when you're using time-shared traps like this. So what people did was developed other methods to actually hold traps, hold particles, and this is actually using light modulators, rather like a data projector, and instead of actually time sharing, they shaped the light beam into multiple patterns or arrays at choice, even in 3 dimensions. And typically this can be done using a spatial light modulator, and that's because if I put a beam in at the side, a displacement in this direction is equivalent to putting a glass prism here. Okay? And so that's a linear phase modulation. A quadratic phase modulation is what a lens does. That gives me light going in and out. So if you like, lenses and prisms like that can allow me to move in 2 and 3 dimensions. And that allows me to create patterns in any direction that I want. And so you can do beautiful things. Here you see there's a huge number of studies done on bacteria, on cell patterning, including stem cell growth. This is just a study in our lab that we did quite a while now ago, where we trap red blood cells, and we can create arrays of them, and then squeeze them and measure them, all just with light. The little white crosses are just actually things for the software to pick up where the laser should be. So there you go. That's what happens. And so you can move them and hold them wherever you like. So that's interesting, but what has interested people, particularly in the last 15 years as well, is how to spin a particle. They might say, why do I want to spin a particle? Well, maybe we want to understand something about the nature of light. We've already heard, many of you know about optical vortices, spin angular momentum, orbital angular momentum. Maybe there's other things you're interested in. Spinning is actually a very interesting degree of freedom. And the angular momentum of light has been a fascinating topic now for over 20 years. It actually goes back a lot longer than that to ideas of pointing and others. But basically, there's 2 ways that we can have angular momentum. Now, why do I need to talk about angular momentum? Because I could make a particle tumble by pushing it in one side, for example, but that's not very elegant and controllable. But if I have what I've done so far, I show you how linear momentum can be transferred to an object. But if I can transfer angular momentum, I can exert a torque. And then that torque will result in a rotation that will be limited to a terminal angular velocity from any drag in the liquid that I have. Okay? So there's 2 ways I could do this. One is I could use spin. So where does spin angular momentum come from? It comes from circularly polarized light. So if you have left or right circularly polarized light, that basically has spin angular momentum plus or minus h bar. God, that's a really small number. But incredibly, you can measure that once again in a room temperature apparatus quite easily. We could also use orbital angular momentum. You've heard some talks even today of optical vortices. These are light fields that have a 0 or a singularity in the middle, and they look like a ring. But the most interesting thing about them is that if you plotted the phase, it would do this. So that's a circle 2 pi. And that's not a discontinuity. That's 2 pi or a multiple. It's rather like going up and down a spiral staircase, like this. And that means, if you look at the scattering force of an object on the surface, it should basically go down like this, like a helter-skelter equivalent. Okay? And that's how that can happen. We won't have time to go into that, but I'll just mention spin. So that's what the spin would do, and spin would always just be spinning, but it's not. And that's orbital, with the phase around the ring. How far do we go back? Well, in fact, today we take these experiments for granted, but in 1936, Beth, in a correspondence with Einstein, did exactly the same experiment. He wanted to measure the angular momentum of light in this very a beautiful double refracting slab experiment here, which is very complicated. So that's the experiment he wants to do. What experiment is that? He's converting angular momentum from plus h bar to minus h bar. How does he do that? He uses an element that probably all of you have used in your lives, a half-wave plate. When you use a half-wave plate, regardless of how you put a half-wave plate in a circularly polarized light beam, you will reverse the handedness. You'll go from left to right or vice versa. You're thinking about that now. You've done it. And when you do that experiment, every time you do that, you exchange 2 h bar. But just like we didn't see our optics move, who's seen their optics rotate? No. No, right. So that's a very small number, 2 h bar, right? So how do we actually see that? So this was a very difficult experiment. But you can swap the world of the very big for the very small. So you can make, so this is probably one of the, so we don't spin golf balls, but we spin trap particles. And this is the first version of that experiment here. And this is incredible. This was a laser crystal that was damaged of calcite. Calcite is birefringent, okay? And you take a fragment of calcite and you tweeze it, and you make it circularly polarized, and it spins. It's the most beautiful demonstration of the mechanical manifestation of polarization of light. Okay? And that was done in the University of Queensland here in Helena Rubinstein Dunlop's group. And the beautiful thing is, that's what the wave plate acts like. Now you might say, well, how do you know it's perfect? You're not going to get a perfect wave plate. It's going to be a little bit of error. You're right. But it's going to change the polarization. So you can decompose it into enough of a change such that there will be a sufficient torque. And then what you do is you put the numbers in, and what happens is you start it spinning, and then in the liquid, what happens? There's a drag. The liquid's not going to stop it spinning forever and ever. You'll get a rotational drag. Where does the drag come from? The liquid. And the rotational Stokes drag is proportional to 8 pi times the angular frequency with the viscosity and the size. If you equate the two, what does this mean? It means you can measure the local viscosity on a micron-sized scale with a spinning bead, just by measuring how fast it goes around. So people have used this for lacrimal or tear fluid in your eye. They've used this to measure the cytosol and many other experiments. So that's a spinning particle. But you can see here, we can actually see that. So this is a liquid crystal droplet you can buy. This is what we get our undergraduate students doing, and they can see it spinning in real time. So it's beautiful. So you can measure that, you can measure it, and actually you can see what the effect it has on other objects around. So it's a rotation of a few radians a second. Many groups have used this for amazing studies. They looked at the twisting constant or the torsional constant of DNA and damage in that. So this is Michelle Wang's group looking at that, as you see here in this paper, using little micropillars for supercoiling torque. And you can do other things. So in our group, we actually used these holographic tweezers to grow neurons. So you can use forces of light used with computer coding on a light modulator, the same as this in our data projector, to force a neuron to grow using optical forces. This actually aligns up the filopodia here. This group here in the US wanted to also direct nerve fiber growth. This was to repair and connect cells with one another. And what they did was they used the stresses created by rotation to force cells to grow in one direction or another. So beautiful things that you can do there. So if I've got 10 minutes or so, hopefully I have. What I'm going to do is talk to you about some directions this field is going in, and that's in vacuum. So everything I've done for the last 40 minutes has been in liquid. Now, why would we want to go to vacuum? Well, we can use these optical traps as amazing sensors. So it turns out they make some of the best sensors we know at all. So this is, for example, a graph of, if you like, volume versus quality factor of a sensor. And they get down to this sort of level, attonewtons. So already 3 years ago, people were measuring down to zeptonewton with a trap sphere. That's 10 to the minus 21. In fact, trapped spheres in vacuum offer one of the most exciting routes to potentially measure gravitational waves on Earth. Now, I'm not going to go into all the details of that, but it's because trapped spheres offer a very small volume but a very high quality factor. Why is that? Because they're isolated from the background. We can get very, very strong constants here and relatively very high Q values. And that's beautiful. So we're an outlier here. That's to be done, and it's at the moment this is way ahead of most systems that we can do. There's another exciting thing we can do in vacuum, and this is one of the things that challenges our everyday understanding of physics, is the boundary between the classical and the quantum world. So you might have heard of buckyballs, you might have heard of molecular studies in the quantum domain. Here, what people are trying to do is take an object that's micron or larger and actually cool it to a ground state. Now, if you can cool it, the occupancy goes as kT over h bar omega, and that means we'd have a microscopic object, and there's even papers describing cells cooled to a quantum ground state in this regime, and the optical traps may offer that. What sort of studies have been done? So let me give you examples. So this is one of my favorite papers in the last 10 years in all of physics. This proves that Einstein's diffusion theory is not the final word. That square root 2 dt is an ensemble. And if you took instantaneous trajectories of a particle here, you can see that that term would explode as t goes to 0. So what happens is here, in this, they actually looked at the instantaneous trajectories with this damping for this particle, and they proved that you had to use basically a Langevin equation. And there's a discrepancy between the motion of this particle and Einstein's diffusion law. This means we now get to the realm of understanding what a quantum particle does in diffusion. This is uncharted territory and will be something where Einstein didn't have all the answers. Very, very exciting. I think one of the most exciting papers I've read in a very, very long time. Okay? Oops. Now, we can also do rotation in space, in vacuum. So I'm going to just show you this video. So this is taken on the International Space Station. Now, this video, I like this video because, well, why do I like this? I like this because it's funny, it's fun, and they're just making a big pass. I don't know how big rugby or American football is. They're doing a pass, and they're doing it because they want to make the longest pass, and they want to get a world record, right? They want to get in a Guinness Book of Records. But the reason I like this video, which very few people pick up on, is that you can see the ball spinning, right? You know intuitively, if I was going to throw a ball to you, a rugby ball or American football, I wouldn't just throw it like that, right? You know intuitively it's going to tumble and it's going to be unpredictable. You know intuitively if you're holding it in your hand, you're going to give it a little twist. Why do you do that? You're thinking about it now, right? You've all done it. What you're doing is you're giving it a privileged axis of angular momentum around which this is conserved, which stops the part thing tumbling, right? Rather like a gyroscope, okay? So what you're doing is you're giving it an angular momentum that must be conserved from here to there. Right, so if I want to throw this water bottle, don't worry, I won't. You know, I would actually obviously twist my hand and spin it towards you. And that would hopefully keep the orientation. That's what they had to do there. So what we did is start to look at this very crazy question about whether the vacuum has friction. And to do that, you need spinning particles. These are all theory papers. A spinning particle next to a surface. This is a beautiful paper in this Einstein-Hopf paper here. And what happens is you've got a Casimir effect of two surfaces attracting each other. But what if I do this? Or I have a rotating body next to a surface. What happens is quantum fluctuations on each side cause an interaction, and then there's a retardation as they can't follow. And that means you get basically a vacuum friction. This is still to be understood and decided on. So what we did was we took a little object and we did exactly the same rotation experiment in a vacuum chamber. And here we made near perfect wave plates. These are little birefringent balls. These are little microscopic wave plates here. And then what we did was we, spun the particle, in the vacuum. Why is that not working? There So there we go. What we do is we put the laser through and we hold it in a little vacuum chamber. And what we do is to levitate the particle, we have a problem in vacuum because we have particles stuck everywhere. So what we do is we use something like out of a singing birthday card, but a lot more energy, a vibrating piece of glass, a piezo. And we vibrate and particles fly up. And we catch one with light. And then we put circularly polarized light and we spin it. And then the only thing we did was suck the air out. We did nothing else. Just suck the air out. Okay? And then you say, how fast will it go? So there we go. And then we just look at the frequencies and what's happening to the particle as it comes through. So you saw 4 or 5 slides ago particles going around at 5, 10 hertz, a few radians per second. So now you're seeing this particle here going at 10 million rotations per second. And a beautiful piece of physics happens here, which is that what happens is, if I was spinning this object here and we sucked the air out of the room, which would be pretty bad for all of us, but what would happen is the mean free path of the gas would become bigger and bigger and bigger and get to a point where it's comparable to one dimension of this object. And then you enter another regime where viscosity is dependent on pressure and the particle goes faster and faster and faster. People have now reached gigahertz level rotation in vacuum with this small trapped particle. And these are making the most exquisite microsensors that we can actually measure for rotational torque in the system. And this is our current status of our experiment, where we're aiming to measure vacuum friction. What we're doing is we're holding 2 particles next to each other, and that's 2 particles in vacuum, you see, and we're actually looking at if the rotation rates change as we put them closer and further away from one another. Now, as you can imagine, there's lots of subtle effects we have to remove, but many groups are working on this, and I think this will be one of the most exciting areas, even if this doesn't need to go to the quantum regime, but can have shed light on whether the vacuum actually plays a role in determining the fundamental rotation rate of particles. Okay, I'm going to end with something completely different, as Monty Python would have said. So our group does lots of things, and this is just to show you thinking outside the box. So 8 years ago, my group developed lots of little fiber chips for trapping, and this was a chip we developed with PDMS and 2 fibers to measure blood. And we did something called Raman Spectroscopy. So some of you will know this. This is a label-free method to give you inelastic scattering of light, which gives you a spectrum, which you can then use. And there's a little chip there. It's pretty small. That's the smallest coin you get in the UK. It's a 1 pence piece. So that was all fine. But then one evening, coming back after a night out, I had a little idea. And what we did was, instead of measuring blood, we measured whiskey, which is a great... so what we did was we actually loaded the chip with a drop of whiskey, and then we took the Raman spectra just with light, and we could tell exactly which whiskey it was just from the light scattering. And this means it's 12, 15, 18-year-old, everything, just from the spectra. So this, for example, 1 whiskey clumped into 3 using multivariate analysis. Now, that was a lot of fun, and it meant that I could legally buy drinks on my research grant, which was great for my group, and only waste a teardrop and have a bottle left in the laboratory. But it actually had a lot of really interesting analysis. So, for example, as many of you know, counterfeit drinks cause a lot of problems around the world. And this technology is now being used in bottling plants in Scotland from a study that I did looking at blood in the beginning. These are some examples of news articles around the world where, unfortunately, bootleg liquor and drinks, if you're not sure what you're drinking, it can actually really affect your life. Anyway, I'll just end with a little video of the whole system. So we took this to a TV.
You can take a sample of it, but you can spit it out. I think there's a spitting spittoon somewhere.
I'm not going to spit it. We're nearly at the end of the show. It's going to be fun.
So Dara, you can taste that, see if you know what type of whiskey it is, and over here the computer is going to have a look at this.
So that's our little chip there.
It's a nice whiskey, Glenmorangie actually. There you go. Right, that's. So we run the light to it.
Now the computer comparing it and says it's a pure malt, correct, but a Japanese
pure malt. Okay, so let's find out if the computer is right, if I'm right. Is the computer right? Yes, it is. Very good. Well done. Congratulations.
So that was a very stressful day for me because, as many of you know, well, having things work in the laboratory is fine. When you go to a place like that with 100 young people jumping up and down, life's not so easy. But it taught us a lot. But it also shows that, you know, in science, lateral thinking and putting ideas together can come from anywhere. So keep your minds open and enjoy what you do. Okay, so with that, I'm going to stop and thank these people for their kind contribution to work, particularly Yoshi, Michael, and Ewan, who did a large amount of the vacuum trapping experiments that you've seen today, and the rest of my group. Thank you for your very kind attention.
Thank you for your excellent talk. Do we have questions in the audience right now? Okay.
Thank you for your energetic talk, really inspiring. And I have a question about the biological part, about the eyes. Is it implemented in medical practice in that method, or is it still in a scientific phase?
Right, so the great question, the question is that method looking at the glial cells,
yes.
Is that used actually in just science, or is it used in, for any treatments at all? At the moment, it's just a research tool to allow us to understand that. They're looking at mouse models and animal models to understand what happens to those glial cells, but it's not used in human eyes, obviously, or it can't be used in vivo or anything at the moment. But it helps us understand eye disease, and the degeneration there, which is obviously a very important thing as people are living longer.
So the next my question is about the principal components analysis.
Mm-hmm.
As you used that analysis, it means that you had a lot of features to measure. And what were the features you used?
Great question.
The
so
PCA.
The question is about the whiskey. So,
yes, about whiskey.
So I'll just repeat this in case anybody doesn't understand. So when you get those graphs, the way we do it is using principal component analysis, which uses something known as a covariance matrix, turns into an eigenvector, eigenvalue problem, and rotates data sets. And each of the PCs picks up, in order, the biggest change in the system.
But,
so the first,
what were the initial features you
right,
used
so the
for
first
PCA?
one is fluorescence. So it turns out when you make Scotch whiskey, sometimes you can tell by eye, right? PT whiskey, if you looked, versus non-PD, like a Lowlands whiskey. You can tell sometimes by eye which drink is which. So really, first one is fluorescence. Then you also have things like congeners. So in Scotland, we make a big deal about the peat and other additives that are going in. And so they have slight changes too. And so those are the things that the PCA picks up. But the training set is on the cloud now, so it picks up exactly all these things very, very well. And in most cases that people want, there's enough of a difference to make the classification.
And about the classification, it was seen that the first principal component caught all the variation, which was...
so fluorescence is really the main thing.
So the fluorescence is the main thing.
That's correct. I didn't comment on this, but also the Raman signal, in contrast, tells you the actual alcohol content. So in Scotland, you cannot sell whiskey unless it's been in a barrel for 3 years and is, I think, 40% alcohol. So the Raman peak tells you the alcohol content, and usually the first principal content, fluorescence, is enough to differentiate. So it's amazingly sensitive to that, and that's enough to use.
Thank you.
Oh, okay.
A technical one. You use macro scale beams like tabletop lasers, and you manipulate with microparticles, usually, yes. What kind of optics are you using to deliver the beams,
Sure.
large beams to small ones? And do you see advantage of 3D printed optics?
Excellent questions. The question is, what optics do we use to deliver the beams, and do we see advantages of 3D optics? So the first part is usually optical trapping just needs around a milliwatts of light in micron size scale beams, micron area beams. So we use usually high numerical aperture optics, like a microscope objective times 100, NA 1.25, oil immersion. And we don't use watts of power. So we want to avoid heating and damage. So we usually try to use the lowest power we can. So all the experiments I showed you were tens of milliwatts, very, very low. Now 3D printed, what people are also doing is to compete with AFM, they're making microfabricated or photopolymerized tools. And what they can do is they can actually make beautiful shapes of tools where they can hook on with light beams, nudge cells, probe cells, and so on. And that's an emergent area. Maybe in one of tomorrow's talks we might hear a bit about that, but it's becoming an exciting area where people microfabricate or photopolymerize tools. They then tweeze inside cells, outside cells. So that's a growth area, and it is happening. But it's in its early stages.
Okay, thank you.
Okay, we have one more question over here.
Thank you for interesting lecture. My question is about laser tweezers manipulation with unit molecular. How much the order of energy that is used for this purpose, and how it is likely to destroy the molecular or ionize it?
If I understand it, the question is, does the energy destroy the molecule or
yes,
the cell
yes,
and damage? Right, so I have some slides on this. I won't go, we can talk about it later, but basically most people usually do viability assays on cells and single molecules, and most people have done studies to show that particularly the wavelengths of 830 nanometers and 970 in this therapeutic window allow little to no damage over 1 hour or 2 hours. But what they do for cells is they do a cloning assay. They hold the cell and then see if the cell divides, basically, and goes down in passage number. Again, if you use the right wavelength and you don't get any photo damage inside the cell can survive for hours, and it's fine. So that's how they do it. It's not perfect. Anything with light, even simple imaging, you have the prospect of photo damage. But if you are doing it in your laboratory, you should do a simple assay like that with the right power levels to make sure the cell survives. You can do stress assays to look at enzymes for stress indicators and other things to see if the cell is basically happy and surviving. And that's the best way to do it.
It is necessary to find a certain frequency for this purpose, yes, if I understand.
To find the right frequency?
Yes.
So many studies in biology have converged on the fact that wavelengths around 780 nanometers to 1100 nanometers are good. In that window, wavelengths like 830 and 970 seem to be very popular particularly. But if you go to the green or the blue, that's obviously damaging to biology. Great for colloidal physics or fundamental physics, but that's where most people, nearly all the biologists work.
Yes, thank you.
All right, do we have any more questions? I have one final question, just to wrap up the discussion. Or did I miss something? Sorry.
Professor, thank you very much for inspiring talk. I have a question about trapping and rotating particles in vacuum, actually, because I was wondering if when you trap particle in optical trap and then suck the air out, do this molecule move around because of sucking air with a pump, or does it not affect
That's an excellent question. So the question is, does the air current, if you like, or the gradient that I cause by reducing the vacuum affect the trap? And if you do it too quickly, the answer is yes. So what we do is we don't just suck it out linearly. We suck a little bit out, let the particle stabilize again, because there is a current, and then we measure the rotation frequency. But you're right, you have to do this very slowly because optical forces are very weak. Vacuum, liquid, or air. And that's a really great question. So what we do is we usually go down and then we wait until the particle stabilizes and the air currents, and then we take the measurements. Okay, but if you do it too quickly, it's very liable, the particle will fall out.
All right, so I can, if I still may, ask the final question.
Sure.
What is your vision in this field of light manipulation, just like a broad picture? Now, we can do all this really exciting science and then the new findings and understand nature better, but from a practical point of view, where would you see this thing coming into practical applications, and where first, and where would it, for example, bring a difference to whatever, chemical manipulation of DNA or other stuff?
Yeah, so I think optical tweezers is always going to be restricted to small numbers of objects. So it's never high throughput, etc. What it might do is look for rare diseases. I think it will help us understand non-equilibrium statistical dynamics of molecules. It's already revolutionized single molecule biophysics. It'll help us understand things like the second law of thermodynamics in more detail, single particle trajectories. And I think in vacuum it will make the most exquisite sensors we ever know. I think you'll see maybe some of the best work from Ashkan is yet still to come. That's what I think. But it's certainly not going to be a tool in every hospital or anything like that. But for very small cells, maybe rare diseases or understanding onset of disease, it could be a beautiful tool. And I think we're starting to see that already.
All right, thank you. Thank you for this super interesting talk. Now the organizers have some presents for you, so yeah, I give the floor to them.
Thank you so much. Thank you.
Before you all go to have your cup of coffee, yeah, we have some updates concerning this evening's social event. Yeah? So, organizing committee wants to give you a chance to enjoy a poster session a little bit longer. So, the scientific discussion between scientists will start at 6 p.m. here at the hall. So, we wait for you to meet you all here and enjoy once again Kishan, Barnell, and Linas Vilchauskas. So, yeah.